Hi there. Well, in the last video, I mentioned a little bit about my experience with Saturn, working at Saturn Corporation doing statistical analysis. And so I wanted to just show you a little bit more about what I did. I had two different jobs there. The first one was in geometric dimensioning and tolerancing, which is also called GD&T for short. And I've just pulled up some different images of car doors. I worked on the doors. So something that I didn't really understand until I worked at Saturn, even though I had a degree, I had a lot of, knowledge in statistics, or a lot of courses in statistics, is that when you're manufacturing parts, they're always going to vary. So for example, if you have this sheet metal, like the frame of the door made out of sheet metal, and this tool is stamping the metal, right? It's stamping it into, like, think of those Star Wars movies, right? Where they're in the droid factories. They're stamping these parts, and the parts are going to wear over time. So they're going to be different. And maybe you have multiple lines, and so those tools are a little bit different. Like the tools are shaped and sometimes like they have to hand grind with a grinder the different surfaces of the tool to make the shape of the door. And then let's say there's a pin, and the pin is like stamping a hole in the part. Well, that pin is going to wear over time. So the pin's going to get smaller. So that means the hole's going to get smaller. Eventually it'll be too small, right? So they're going to have to replace that pin. And then at some point, well, let's say they don't get the pin in the exact same spot. So that location of the hole could vary a little bit. And different different pins might move around and all that. And again, if you have multiple machines, like multiple presses stamping, then you're going to have slight variation from line to line. So one of my jobs at Saturn, the first one, was to put these tolerances on the blueprint. So let me see if I can find a good picture. Like, this isn't necessarily a door here, but this is like an example of a blueprint where you have all the features, and we would have to decide, okay, what's the tolerance? How much can this whole location vary? Or how much can the diameter of the hole vary? And still be able to put the car together? And then it still has to work, right? And it needs to look good. So you don't want it to look like it's just all cobbled together, right? So it's amazing how many parts there are just in a door itself. And then you got to put the door on the car, and you want all your fit and finish. You want your gaps to line up nicely and be parallel. You don't want your doors like this or like that. Same with aligning with the fenders and all that. So we would do what's called a tolerance stack, where we would take the tolerances, we would put the tolerances on the blueprints, but in order to understand how much variation we could have in each individual part, we need to look at the overall variation in the system. So we would go, let's say, from one door to the other door. I think I have sort of an assembly picture here somewhere. Oh, I may have lost it. Oh, looks like I lost it. Well, so imagine the side of a door here. This is the one I was thinking of. Here's the frame of the body, and then you're putting the doors on. So you've got multiple layers in the door, because you've got the frame, and then you've got the hinges and the exterior panel, the handle. Then you're going through the hinge to the frame to all the parts, on the frame here. So what we would do is we would use a formula for the variance, where you add up the variances and then take the square root. We're not using that formula in this class, but we would add up all those variances, essentially get the variation of the assembly and then make sure that that meets the specs for the outer specs, the gaps and things like that, and then translate that down to what do the individual specs need to be. Okay, so that was one job I did, and that was in dimensioning and tolerancing. And then the other one was reliability. So they also want to make sure the car is going to work, right? So they test all the parts of the car. They test the seat belt, it's like a simulation, but it's a real, test. And I found a door, like a door fixture here. So this is a company that actually like just has this fixture, and they just open and shut the door over and over and over again and see when it starts to break. Okay, so this is called reliability analysis. This job was often a fight over sample size because this testing is really, really expensive, as you can imagine. Let's say this machine is just slamming this door, 24 hours a day for like weeks or months on end. So that testing costs a lot, and it takes time too. So they would want to test like 2 door panels, but you're like, 2 is not a sample size that you can do anything with. So it's a little challenging, is fighting over sample size. But imagine a fixture that like just, pulls a seat belt over and over and over again. And here we often use the Weibull model, which is a time to failure statistical distribution. So there's a lot of great and interesting things you can do with statistics. These are just 2 in manufacturing. And that's not even, this is in the engineering and design of the car. There's also the actual plant or factory where you could think of statistical process control. So as the manufacturing process is happening, then they use statistical process control to measure things periodically and see if things are getting off or not, so that they can correct things that are happening as soon as possible. So that's another area that's super interesting, but I didn't get too much involved in that. So that's a little bit more of a couple ways you could use statistics in the design or engineering phase of a product. Okay, thanks for watching.